Hello, good morning, everyone. So, again, good afternoon, everyone, and thank you for your patience. We apologize for the slight delay due to an unforeseen technical glitch. So, it's my pleasure to introduce Dr. Raghuram, who is an assistant professor in the Department of Civil Engineering at BITS Pilani, Hyderabad Campus. Dr. Raghuram obtained his PhD in geotechnical engineering from IIT Hyderabad and has held postdoctoral position at IIT Bombay and Aalto University, Finland. His research focuses on sustainable geotechnical engineering, including carbon negative ground improvement techniques, sustainable geomaterials, slope stability, and risk and reliability analysis. He has published more than 35 research papers, secured research funding exceeding 1.2 crores from agencies such as ISRO, NBCC, and TTDF. In today's talk, Dr. Raghuram will discuss the application of capillary barrier systems for mitigating rainfall-induced landslides. The presentation will explore the use of municipal solid waste incineration, bottom ash, as a sustainable alternative to conventional coarse-grained materials in uh, capillary barrier systems, highlighting the underlying mechanisms, experimental investigations, and its potential for enhancing slope stability while promoting sustainable engineering practices. Please join me in warmly welcoming Dr. Raghuram. Dr. Raghuram, your turn.
Thank you for such a brief introduction. Good afternoon, all. In today's talk, I'll be covering about how we can reduce the risk during the landslides using specifically this capillary barrier systems. So my presentation goes like this. First, I will introduce the topic, and then we'll see the mechanism that is involved in the landslides and what are the existing slope stability techniques and capillary barrier system. What is the mechanism involved in capillary barrier system, and the studies that we are conducting at BITS what we have already conducted in BITS regarding this experimental program and numerical modeling, and finally we'll conclude. So if you look at it, this particular chart, most of the slope failures or landslides are due to the rainfall, where we can see 46% of the failures are due to rainfall, and we can see that it's a main triggering factor. Afterwards, we can see the engineering activities like constructions, etc. And from this Geological Survey of India, in 2022 to 2015 to 22, especially in India, we can see the hotspots where the slope failures or landslides have been taken place in this particular zone. And this is what happens when there is a rainfall. It flows as a runoff, and the soil particles will erode. The water will carry the soil particles along with it, and it initiates the triggering factors. So when we talk about the climate change, we have seen climate change. This particular thing changes the intensity and duration of the rainfall. Whatever we are expected rainfall intensity, it's being crossing the expectation limits or maybe lesser than the expectation limits. And duration, especially these days, we are seeing of increasing durations, and all these things are due to this climate change. Of various activities. And if you look at the number of incidences with what are the failures across the world and the Europe, you can see most of the unusual rain. So here you can see in the worldwide, it is almost 35 incidences in 2018. And what happens when rainfall is there? When rainfall infiltrates into the soil, it increases the pore water pressure, due to which the shear strength will reduce and slope failure triggers. So here I have shown some of the slope failures that we have, landslides we have witnessed in India and abroad. Few slope failures or landslides in Kerala, Wayanad landslide in 2024, Taiwan in 2010, and Uttarakhand landslide. This is the one of the devastating landslides in 1970, and again recent Uttarakhand 2021, and Singapore slope failure in 94. So if you look at the global scenario, This is how the landslide potential activity changes with respect to the time. In you can see the hotspots in maybe in June, July in India, and where you can see the northeastern part and the some part of southern part of India are being prone to the slope failures or landslides. So here, this is the zoomed version of the same thing I have shown here. You can see the you can notice devastating failures across the India. So, if we look at what is the mechanism that is involved, this is what it happens. So, when there is a rainfall, initially the soil is in dry condition. But when the rain infiltrates into the soil, what happens is the soil becomes wet and slowly the pore water pressure develops. It increases the pore water pressure, and this pore water pressure pushes the particles away. And you can see the slide. So this is the water. Initially, the water is slowly getting penetrated into the soil, and this gives a single push and it initiates the slope failure. So if we look at the soil zonation above the water table and below the water table, here we have three components. One is water, soil particles, and air particles. This we call it as unsaturated zone because it's not fully saturated. We have some air voids. Below the water table, all the pores in the soil are completely filled with water. So here we experience a positive pore water pressure where it pushes the particles away. Whereas here we can expect a negative pore water pressure that we call it as suction. So during rainfall, what happens is this negative pore water pressure turns to positive. So that means this again, whatever that is there in the unsaturated region, slowly all the pores are being filled with water and the pore pressure increases. During evaporation, it further goes down. That means it further goes negative. So the soil should be treated, the slope should be treated as integral part of both unsaturated and saturated soils. So here, I have shown the same thing here. Most of the geotechnical infrastructure lies above the water table, that is in unsaturated region. If you look at the zoomed version of this one, we have air particles, soil particles, and also water molecules. But below the water table, all the pores are completely filled with water. So when I talk about unsaturated soils, here it contains a total section which is summation of matrix section and osmotic section. The name itself is indicating matrix section means it is due to the soil particles, the particles of the soil, and osmotic section is due to suction that is related to presence of salts. But here, when we are talking when we are dealing with the flow conditions, we can always concentrate on matrix section, which is pore air pressure and pore water pressure, and this is how the suction exists between two soil particles. And generally we all know that soil is a three-phase system, that is air, water, and soil particles will be there in the soil. However, there is one more phase, that is contractile skin, that is a phase that is between air and the water. It's an interface between air and the water. However, physical subdivision is not necessary. That's why we are still dealing with three-phase system. If I take a simple slope like this, and if you assume this as a water table, blue one is a water table, and what happens is during this increased pore pressure, it pushes the particles away. That means each particle is getting pushed each other. But in the suction or during in the unsaturated soils where you have some air pockets, some water molecules, some soil particles, it pulls the particles together and increases the strength. So there exists a unique relation between soil suction and volumetric water content or water content of the soil that we call it as SWCC, soil water characteristic curve. So here in this, if I measure this SWCC, it appears like this. There are several ways to measure SWCC. I'm not going in detail how to measure this one, but I'll try to explain what are the different regions associated in this region, in this plot. So first one is boundary effect region. You can see that all pores are completely filled with water. Here, some air pockets are there. In the third phase, residual zone of saturation, you have very less water and more air in the soil. So what happens is, in the first case, when degree of saturation is unity, water tries to go to the other end easily. It finds its path very quickly. But in the transition region, you have some air pockets. So it travels the longest path or it travels very long way to reach the other end. However, it reaches the other end. In the last case, the residual zone of saturation, water cannot move at all because most of the predominating part is air here. It's all, we can almost say that it's completely dry. Okay, here we have two different models that are commonly being used in soil mechanics, saturated soil mechanics, Ragland and Zing and Manganesian models. I'll show here what are the models and the associated equations. Here, the psi represents suction and theta W represents volumetric water content. So here you have A, N, M parameters as a fitting parameters for this Ragland and Zing model, alpha N parameters as fitting parameters for Manganesian model. So we are using these two models in the study. And now, what are the existing slope stability techniques? We have various slope stability techniques like terracing, retaining walls, rock bolts, geotextiles, vegetation, etc. You can see here soil nailing. Here, this is again a vegetation with a green mat. This is one more technique with conventional geosynthetics, and this is geomat. This is with the geocell. Everything here, all the techniques are applicable for a site specific thing. Each technique is a site specific. We have to choose wisely all the techniques. Okay, here some more measures are there that are like a surface drainage where we can divert the water rainfall that is there. The second one is subsurface drainage where you can lower the water table position, because when you provide a subsurface drainage without any clogging, water will go out easily. And then you can, this is a geometric modifications, like you can, if there is a steep slope, always what you can do is you can trim the slopes in certain with some benches so that the stability will increase. And here retaining walls are there to counteract the slope activities, and then reinforcing systems like soil nailing, as I mentioned, geocell, and then vegetation, and then soil ground improvement techniques by providing piles or maybe drill shafts, anything. And the last one is capillary barrier system. So here capillary barrier system is something like we will be providing some different layers on top of the existing slope so that the water will divert from the slope and we retain the yeah, all the soil or slope material in unsaturated conditions. So here I have summarized some of the slope stability techniques like surface drains. What are the advantages? Controls infiltration. Yes, it controls, and but it doesn't increase any of the factor of safeties. Similarly, soil nailing, it cannot control anything here regarding the infiltration or pore pressure, but it reinforces the soil. Here in capillary barrier system, yes, it controls the infiltration, it reduces the pore water pressure, it reinforces the soil. How it's reinforcing? It indirectly reinforces the soil. I'll explain how it reinforces the soil in the coming slides. So here, what is the mechanism that is involved in capillary barrier system? Let us say this is the existing slope or soil slope that we have. So I want to preserve these unsaturated conditions, because in unsaturated conditions, as I mentioned in earlier slides, it pulls the particles together and the strength will improve due to matrix suction, right? Now, if I can preserve these unsaturated properties, the slope will be in stable conditions. So how we can preserve? By providing some alternate layers of coarse grain soil and fine grain soils. So here what happens is when there is a rainfall, all the rainfall will go as a runoff. Okay, most of the soil will go as a runoff and it will be collected at a collected drain. And because of this because fine grain soil has a very low permeability, and it will not allow the water to penetrate easily into the soil. So alternatively, we have coarse grain soil. So even if some water is getting percolated, that will be going to the discharge units there. So here, yes, in some of the countries, they have already used this technique in Korea and Japan, OITA, where they want to preserve some historical structures with these CBS techniques, where they have provided with alternate layers of coarse grain soils and fine grain soils. Now, what are the challenges and what are the opportunities that we can see? Here, one of the challenges, if even if we provide this capillary barrier system, if the rainfall is very intense, let us say than very expected, 10 times expected or 15 times, and that too with a prolonged duration, like maybe 1 day, 2 days, like that, then of course the water will slowly penetrate into the soil. And what are the opportunities? Yes, we have material innovation, meaning conventional CBS has clay particles, which is a fine grain material, which can be where we can use clay, silt, or fine sand, and coarse materials we have to use coarse sand or maybe gravel. Instead of going for conventional soils, we can always think of existing alternative materials. We'll be discussing about what are the existing alternative materials. and there's a eco engineering approach, and we can apply to any of the global conditions. So here, while coming to the bottom municipal solid waste incinerated bottom ash, here we are considering incinerated bottom ash as one of the primary source for this CBS material, because we want to replace the coarse sand, because we know the uh, scarcity of the sand and the problems associated with the sand. So that's why we want to replace the coarse sand with the municipal solid waste bottom ash. Here, with increasing population, always the municipal solid waste will increase. So with increasing the waste, whatever right now what we are doing, we are simply dumping the waste in the municipal solid waste dump sites. So here the waste will be generated and it will be collected. So here after the collection it will be incinerated, and bottom ash will be getting generated. We will be collecting that bottom ash and we are characterizing the material, and we are reusing for this these kind of techniques. This is how the bottom ash looks like. And why only bottom ash? As I said, abundant supply. Because with increasing population, the waste will increase and obviously the ash will increase. Now, we have chosen particular landfill because near to BITS Hyderabad campus, we have a Jawahar Nagar landfill. And fortunately or unfortunately, it's one of the fourth largest methane emission gas landfills in the world. So here, if you look at the statistics, from 2015 to 25, the municipal solid waste capacity has drastically increased. I can say almost it's doubled. For 3,500 to 3,800 to almost 8,000, it has reached municipal solid waste tons per day. And here, what we are doing, we are trying to utilize the some of the waste for this incinerated bottom ash, and we are converting that waste to energy kind of thing. And this is how it goes. As I said, waste generation, segregation, collection system, transport, and then waste recovery, and then finally dumping into the. If we use some of the material, we will be using that. Otherwise, again, it will be going disposing to the landfill. And you can see here the topmost left hand side, this is the one of the Jawahar Nagar dump yard, municipal solid waste landfill here. And once the waste is getting dumped here, it will be collected to the collection tanks. And here you have a wet stage and then dry stage. It will be dried before sending it to the incinerated. So once it gets incinerated, some of the power will be used to for the power generation from the gases that are emitted, and rest it will be disposed as a municipal solid waste bottom ash. Now, here in this bottom ash contains various fragments of this one, aggregates, ceramic tiles, stones, etc. So based on this, we have segregated the waste, and we are using the for particular technique for capillary barrier system. So this is my slope, and here instead of going for conventional sand, we are utilizing municipal solid waste bottom ash. On top of which we are providing a fine grain soil, and this vegetation is optional. If we want to avoid any kind of erosion, we can go with the vegetation, or simply we can provide a simple blanket of geotextile or jute geotextile conventional things. So, what is the advantage of going with the municipal solid waste bottom ash when compared to conventional materials like aggregates? So, as I said, natural aggregates or coarse sand is costly. First thing. Second thing is here we have well-established performance, but here this can be studied, and then we can match the consistency of this municipal solid waste on par with the coarse sand or maybe aggregates. And while here, as I said, it's very costly. It's not economical, but it's very cheap. On top of that, we are utilizing the waste and we are converting the waste to energy. That's the main thing what we are doing. Now, if you look at the existence of this capillary barrier system in 98, Stormont et al. 98, they have utilized this capillary barrier system for this water storage facilities. After that, Indravan et al. Has studied he modified the residual soil for fine grain soil. People have started redefining the capillary barrier system with various techniques. And while coming to this potential use of this residual soils, Grinsani in 2006 has studied this one, and Rahajato, he is the one of the pioneers in this area, where he has developed alternate layers of this fine grain soil and coarse grain soil for this capillary barrier system. So you can see most of the studies by Rahajato et al., Satyanaga et al. Satyanaga, Rahajato, they have studied, they have conducted numerical analysis also, how it works under extreme rainfall conditions. And in 24, yes, they have used it for extreme rainfall conditions to stabilize the slopes. Now we are using the same technology, but instead of conventional techniques, we are proposing this new techniques with used materials. or ash. So here our objective is to characterize the sand, municipal solid bottom ash, and then first we have started with laboratory scale studies, and after once the studies are completed, we'll proceed to we'll apply the same technology to the field as well. We are planning to do that. And then numerical modeling using geoslope geostudio. So here we have procured river sand as the main slope material and clay as a fine grain material. Municipal solid waste bottom ash is a coarse grain layer. And with rainfall, variable rainfall intensities, variable slope angles, different layer thickness, we are studying the things. And this is how it goes. A methodology we'll be discussing one by one. So experimental program. This is the grain size analysis of the sand that we have used in our study. And this is the bottom ash, particle distribution of the bottom ash. You can see poorly graded sand. And these are the segregated ash with the different sizes. You can see this one. And these are the properties of sand, clay, and the bottom ash that we have used in the study. Now, while coming to the experimental setup, yes, we do have this rainfall setup. We have fabricated the test with a 1 meter length and 0.7 meter width and 0.8 meter height. So here you can see different. We have five different pressure gauges attached with the nozzle so that we can monitor the pressure. We want to see the mechanism that is being applicable for all kinds of rainfall intensities: moderate, severe, moderate, high, and very severe rainfall intensities. So we are using metro meters, Teros 12 moisture sensors, and 21 matrix action potential sensors, and ZL6 data logger. All the data is being stored in this data logger. So once the soil is laid here, the slope, you can see this. This is how it appears. This is the sandy slope with all the sensors inserted. We have put the sensors in both the sides, right and left directions, at various depths, so that we can monitor the level of water. And this is the municipal solid waste layer, and this is the soft clay, fine grained soil. And this is how the rainfall occurs. So while coming to the experimental setup, yes, we cannot have a slope at a single stretch. That's why we have been following this construction. We are constructing the slope in a stepped manner, meaning you can see this one. This is the stepped slope. After the once you construct that, you can chip off the additional portion. So this is the during the initial stage of the construction of the slope, and this is the final stage of the after the construction. You can see some of the sensors that are being inserted on both the directions at the different depths. And this is how it looks from the side view, step by step procedure with different layers. After placing the layer, you can chip off this one and you can see this one. And now for 30 we have, as I said, we are monitoring this for various slope angles with various rainfall intensities. So here you can see this is a 30-degree flat slope, and this is just before the rain exposed to the rainfall. This is after the rainfall. You can see the slope failure. This is for 45 degrees and the associated slope failure. This is for 60 degrees, very steep slope, and for the associated slope failure here. And if you look at it, we have monitored, I'm not presenting all the results here, but I can show you the SWCC, which is the relation between, as I said, matrix section and the moisture content. Here in 45 degree slope, 8 hours 30 minutes, heavy rain. So this heavy rain, heavy showers and severe rain, we have considered this terminology from the IMD department, Indian Meteorological Department. So heavy rain means the intensity of rainfall is 1 to 2 centimeters per hour, and this is heavy showers means 2 to 4, and severity means it indicates greater than 5. So here you can see the matrix section. This is almost, it's most of the sensors have reached 100 kilopascals, whereas here it is just 10 kilopascals. That means the matrix section is almost negligible. And heavy showers, that means during heavy rains the matrix section, this is without CBS. Okay, so the slope cannot able to maintain the matrix section, or the maybe we can say that all the pores in the soil are filled with water. Now I can show you this one. It's not moving. Actually, this video contains with the movement of the water, it is also carrying out the particles along with the water. So we can see the erosion, how the slope erodes in this particular thing. So here, along with the water, it also carries the soil particles or grains along with it. This is without CBS. So here, the same thing we have done it for with CBS in the stage technologies, in the stage construction. This is for again the same 30-degree slope. This is for 45 degrees with the same one. Here you can see the CBS material. Once it is laid completely, we have laid the fine grain material. And at the start of the experiment, it looks like this. And even after the 5 or 30 minutes of rainfall, you don't see any slope failure here in this case. That means you can say that most of the slope or most of the slope is intact, and also you can see the matrix section is being preserved under the slope. That means we can say that the slope is stable. So here, if you look at the same matrix section and moisture content sensors readings, here with CBS, you can see the matrix section is 1000 kilopascals. Without CBS, as I said, it is just a few 50 tenths of kilopascals, like 70, 60 or 70 kilopascals. So here, due to the CBS, this particular capillary barrier system, the rainfall infiltration is getting delayed, and it because it provides a lateral drainage for the water to flow, and it preserves the matrix section by providing additional reinforcement kind of thing, and it maintains a higher unsaturated shear strength. When matrix section is higher, shear strength will be obviously higher. So the same thing we have carried out in numerical analysis. As I said, we have seen heavy rain, heavy showers and violent rain as per IMD data for 30, 45, 60. We have also done the analysis for various slope inclinations like 35, 40, 45, 50, 55, 60, like that. We all familiar with this factor of safety equations. This is the only additional term that we are considering, chi into UA minus UW. That is the unsaturated shear strength associated with the slope. So we have used this Bishop's extended principles for this one, and we have followed we have followed GeoStudio for carrying out this analysis. You can see this is for 30-degree slope, this is for 40, this is for 50. This is bare slopes. These two are bare slope. This is with CBS, layers of coarse grain soil and fine grain soil. Whatever the parameters that we have found out from the experiments, that we are giving it as an input in this GeoStudio so that we can replicate what is the factor of safety. You can see that with CBS 60-degree slope, the factor of safety is 0.87, which indicates the hazardness of the slope or indicates a failure. Whereas here with the same slope with CBS, the same 60-degree slope, it is indicating a factor of safety of 1.62. It's a bit on higher side, meaning it thus indicating the risk much more higher than the driving forces. So here one more interesting observation is we are also varying the thickness of the each layer. Here you can see the thickness of this coarse grain layer is like much lesser than the thickness of the fine grain layer. Here it's vice versa. But interestingly, the factor of safety in this case is much higher when compared to this low thickness of the fine grain layer. The reason is when you have a high thick fine grain layer, water will most of the water will go as a runoff. Therefore, we can expect a higher factor of safety when compared to the other case. So this is the significance of the study. We are trying to look at how we can utilize the municipal solid waste bottom ash in our to stabilize the rainfall slopes failures. Here we are providing. See here, this particular incinerated bottom ash comes in different sizes. Okay, we can use it as a fine grain layer. We can also use it as a coarse grain layer depending on the particle size distribution. So here in this particular study, we are utilizing it as a coarse grain layer. Okay, if the bottom ash, the particle size depends on the temperature at which the ash is being burnt, okay, or maybe the municipal solid waste is being burnt. If it is higher, we get a more fine material. If it is a bit lower, let's say some 800 degrees or 1400 degrees, we get a coarse grain layer like that. So here in this particular study, we are utilizing it as a coarse grain layer. So again, it's so that we are trying to utilize the bottom ash for stabilizing one of the major concerns that we are dealing in our country. So, while coming to the conclusions, here I can say that the matrix section is being preserved under prolonged rainfall, and again, the thickness plays an important role. The thickness of each layer. So, we can come up with optimum thickness values also, and if we increase the thickness of the fine grain layer, it's more stable when compared to the thickness of the coarse grain layer, and here this one of the major advantage of this capillary barrier is it alters the seepage issues because it provides most of the water as a runoff. Okay, so the water penetration into the soil becomes very less, and this is a viable technique and sustainable alternative to conventional materials. As I said, if we use coarse grain soils or conventional soils, it's always cost effective thing, and also it's not scarce materials. So like sand, nowadays we are not getting sand, so people are always looking for alternative materials. So I would like to acknowledge my co-PI, Professor Anasua, a Professor Department of Civil Engineering, and Kuntala Bhushan. She is a scientist from NESAT, and this project is being funded by ISRO. So she is the ISRO coordinator from ISRO side, and Lakshmi Prasanna, my PhD student, and Sai Srujan from our BA student for carrying out this analysis. These are the references. Thank you. If you have any questions.
Thank you very much, Dr. Raghuram, for excellent and insightful talk. So we appreciate your valuable perspective on sustainable slope stabilization and this capillary barrier systems. I have been visiting the mountains, and I've been always been curious how do they and why they would patch the mountains such a way.
Yeah.
Well, on behalf of everyone present, I would like to thank you for sharing your expertise today, and we look forward to your future contribution and wish you continued success. Thank
My
you.
pleasure. Thank you. Thank you very much.